Hey kids, I hope you're enjoying this radical chapter. We've done multiplying, addition, subtraction, so that leaves dividing with radicals. So this is probably the trickiest of all of them, but not too bad if you've been doing the work leading up to now. Division is essentially the same rules as multiplication in math. It's the inverse operation, so it's the other side of the coin, if you will. So let's just talk about what we know about multiplication very quickly. You can take any two square roots and multiply them together and put them under one big square root. And you can also go backwards. If you have a big square root, you can break it up into two. That's what we do when we reduce radicals often. So you'll find that that is helpful to go this way and that way sometimes with division. If you're dividing two square roots by each other, you can put it under one big and divide the two numbers. Likewise, you'll have to, from time to time, go the other way. If you have a fraction inside, you'll have to break it up and do two separate square roots. And we'll talk about why that is. Part of it is just, math grammar. But here are a few rules for your square root answers to be totally in complete simplified form. Number one, we already know that all perfect squares must be factored out of the radicand. If you can reduce that square root, always make sure you're done. Don't leave root 8 in a final answer. You can take out root 4 or vice versa. But now that we're talking about dividing, you're going to run into fractions. And one thing, you can never leave a fraction under a radical sign in a final answer. So in other words, you could never leave this because they're expecting you to break it up and deal with them individually. And another thing you're going to run into is you cannot leave a radical in the denominator of a fraction. So no radicals left in the bottom of a fraction in the final answer. And we'll talk about how to deal with that, but at least know that going in. These are the things we're talking about. Okay, so to warm up, and it's related to what we're doing today, let's talk about these. We talked about multiplying these square roots, but this is a specific property, multiplying a square root by itself. Square root of 2 times square root of 2. Hopefully you've made that connection that that's joined to be just regular 2. Root 2 times root 2 is 2. If you need a reminder of why, that means because your root 2 times root 2 is root 4, and the square root of 4 is 2. But that happens every time you do a square root times itself, right? Square root of 15 times the square root of 15, it's going to be good old regular 15 because that's 15 squared, and the square root of 15 squared is 15. I mean, again, you can just trust that idea that, hey, the square root of something squared is that thing. So they're canceled. If you want to actually do it, the square root of 15 squared is the square root of 225, and then that's 15. But it's kind of nice to trust this rule you're going to see later today. Root 237 times root 237. I have no idea what 237 squared is, and I don't need to. I know this answer is going to be 237. Again, because what's under here is just this number squared, and the square root of that squared is that number. Okay, so there's a lot of little twists and subtleties with these, so unfortunately I do have kind of a bunch of examples to run through, and each one has little twists, so really try to hang through to the end of this video today. So right now we have root 50 divided by root 2. Now since they're both square roots, my first idea is, why don't I just try to divide them by each other, and especially I notice 2 goes into 50. So I could take this step and write this out. That's really just the square root of 50 divided by 2. See, I'm putting them together under one big square root. 2 goes into 50, 25, and now you're dealing with the square root of 25. And we know how to deal with that. The square root of 25 is 5. All right. What about when they've got coefficients out in front? No big deal, just like with multiplying. You divide the radicals by radicals and the non-radicals by non-radicals. The coefficients. 21 divided by 7 is 3. Root 60 divided by root 3, since I notice 3 goes into 60 evenly, is root 20. Hey, cool. Done? No, root 20 is not a perfect square, so we're going to reduce that however you like to do it. I think a lot of people are on board with the perfect squares method, that root 4 goes into root 20. So 4 is a perfect square. The square root of 4 is 2. And then you have root 5, and then 3 times 2 root 5 is 6 root 5. There is your final answer. Okay, root 5 cannot reduce anymore. Okay, number 6. We're starting off with a fraction inside of the square root. Notice the fraction does not reduce. That would be my first thing to check for. 4 doesn't go into 25. And so you cannot leave this that way in math. It's bad form. You know, if you're at a math party, it's just bad grammar, bad form to leave it that way. No fractions left inside of a radical. So this is where we're going the other way with it and breaking it up into two separate square roots. Square root of the top over square root of the bottom. And then you deal with those independently, you know, individually. Square root of 25, hey, that's perfect square, 5. Square root of 4, perfect square, 2. Done. Easy. How about the square root of 27/16? 16 doesn't go into 27, and the fraction doesn't reduce in any way. So, can't leave that fraction inside. We break it up into two separate square roots, and you deal with these individually now. You'll notice 27 is not a perfect square. 16 is. So one thing, I'm going to just make that denominator 4. The square root of 16 is 4. Boom. No square root sign left there. Square root of 27, not a perfect square, so this is where you're going to, you know, do your reducing if possible. Any perfect squares go in. 9 goes in. So root 9 times root 3, the square root of 9 is 3, and root 3 is left over. So here's what you have right now. We have 3 root 3 all over 4. And of course the big question as you're doing these and you're a little unsure, if you haven't been doing them very long, is am I done? Can I move on, or can I go further? And the things to check for are, is your radical reduced? You know, root 3 cannot reduce anymore. We're good there. Are there any radicals in the denominator? No, none, so we're good there. The other thing is to just look at these non-radicals here, the fraction 3/4. You know, that's just the fraction 3/4. Can that reduce in any way? 3/4 does not reduce. So you're good to go. That is your final answer there. Okay, so we're going to do the flip side now. And yeah, I know there's a few more examples because trust me, there's a couple weird things we're going to get to. But you know why plants hate math? It's because it gives them square roots. It's terrible. Definitely doesn't work over YouTube. It doesn't even work in the class, but it's even worse here. So number 8, we got 1 over root 2. Root 2, not a perfect square, can't reduce in any way, seems to kind of be done. There's not a whole lot you can do, except this rule on the front that you cannot leave a radical in the denominator of a fraction. I can leave a radical in the numerator. In fact, I just did on the previous problem. But this rule here, no radicals left in the denominator. We don't like to have irrational numbers. That's what a radical is, an irrational number left in the denominator. So what I'm going to do is do this process which is called rationalizing the denominator. And if you know from your fraction work, like when you make common denominators and things, you can multiply a fraction by anything you want in the denominator as long as you multiply the top by that same amount. And so this is really where that warm-up comes into play. And here it is actually. In the warm-up, we had root 2. We made it be 2 by multiplying it by the same square root. Root 2 times root 2 gave us 2. No radical left over. So I'm going to use that process right here. I'm going to use that trick. Well, hey, I could change this to 2 if I multiply by root 2. And so I'm allowed to do this in math as long as you multiply the numerator by the same amount. So if I multiply the bottom by root 2, I got to multiply the top by root 2. And now just got to be careful with your math. You know, lots of silly mistakes can happen here. Root 2 times root 2 is 2. It gives you root 4, and root 4 is 2. And in the numerator, 1 times root 2, we've been multiplying radicals now. 1 times root 2 is root 2. And now you have this. Does root 2 over 2 reduce in any way? No. And if any of you are tempted to divide 2 by 2, keep in mind you can't. That 2 is inside that square root. You know, it cannot be divided by non-radicals. So you have that. And if you like, again, on your calculator, check 1 divided by root 2. See what decimal that gives you. If you do the square root of 2 divided by 2, it's the same decimal. You haven't changed the value, just expressed it with a rational denominator. That's that. All right, number 9. So now we're going to mix basically all these little properties together. Root 4/5, can't leave a fraction, so I break it up. Root 4 over root 5. The square root of 4 is 2. Root 5, not a perfect square, doesn't reduce in any way, so this is where I can't leave that radical. I'm going to rationalize the denominator. You got to get that vocabulary down for your next math party. You want to sound intelligent when you discuss these things. So I'm going to multiply by root 5 to rationalize that, and then you've got to do the same thing to the top. Multiply that by root 5. So in your denominator now, root 5 times root 5 gives you 5, good old regular 5, you know, root 25, which becomes 5. In the numerator, 2 times root 5, that's a non-radical times a radical. That's really just like multiplying 2 by the 1 that's out in front. 2 times 1 is 2. You have 2 root 5 over 5. Final thing, can this reduce in any way, shape, or form? Root 5 certainly can't. Look at your ratio of these non-radicals, 2/5. 2/5 cannot reduce. That means your final answer is completely reduced. Not too bad, but a little weird, and you're putting a lot of little properties and ideas together, and lots of little room for careless mistakes. But nothing that's beyond you if you'll just, you know, slow down and take your time. So here we go again, number 10, a fraction inside of a radical. I can't leave that. 5/3 doesn't reduce. Break it up into 2 separate square roots. Root 5 over root 3. Neither one is a perfect square or reduces. Can't leave a radical in the denominator. So I'm going to multiply by that same root 3 to rationalize. And if you multiply the bottom by it, you got to multiply the top by the same amount. Now in your denominator, root 3 times root 3 gives you 3. Root 5 times root 3 in the numerator, they're both square roots, so I can multiply them together and put them under one big square root. Root 5 times root 3 is root 15. And now, can this answer reduce? Don't try to reduce 3 into 15, because that's inside of a house there, inside of a square root, and that is not. That's a radical, that's a non-radical. But can the root 15 reduce at all? Nope. No perfect squares go into 15. That answer is completely reduced. Root 15 over 3. This right here, number 11, 10 over root 6. 10 and 6, you cannot reduce those because, again, that's outside of a radical, that's inside of a radical. So, you know, they can't mix, you know. Root 6 does not reduce. It's not a perfect square. I can't leave a radical in the denominator. I'm going to multiply by root 6 and numerator by root 6. So I'm really multiplying by root 6 over root 6, which again is, the reason you're allowed to do this, think about it, is root 6 over root 6 is really just 1. So you're just multiplying the fraction by a special form of 1. What does it give you? In the denominator, root 6 times root 6 is 6. Numerator, 10 times root 6 is 10 root 6. And now take a look at that. Root 6 cannot reduce, but look at your non-radicals right here. 10/6. That fraction can reduce. You can divide each by 2, and you still are going to have the root 6 there. That's not part of this reduction. You're just reducing the fraction 10/6. They're both divisible by 2, so you get 5/3. So 5 root 6 over 3. And I would say right here, like the difference here is something to watch. Kids are sometimes a little careless when they go multiplying. Root 5 times root 3 gives you root 15. Because you're multiplying 2 square roots to each other. This is just 10, not root 10, times root 6. you cannot multiply them together. So sometimes kids look at me, root 60 or things like that. It's just 10 root 6. So just pay attention to what you're doing and you'll be fine. Last two examples just to see hopefully that you're comfortable. If you want to pause and try this, if you're even still watching this video. 6/7 doesn't reduce, root 3 doesn't reduce. It's not a perfect square. I can't leave it in the bottom, so I'm going to multiply by something to rationalize it. You don't need to multiply by 7 root 3. It's just the root 3 that is troublesome. So I'm going to multiply by root 3 and root 3. What does that give you? In the top, 6 times root 3, again, that's a radical times a non-radical, just gives you 6 root 3. In the denominator, be a little careful because of that 7. That's 7 times 1, that's really out in front, so you get 7 times root 3, which is 3. So now you really have 7 times 3 in the bottom, and you'll have 6 root 3 over 21. Is that done? Can it reduce? Take a look at that ratio right there, 6 over 21. Those are both divisible by 3. And that will give you 2 root 3 over 7. Done. 2/7 can't reduce, root 3 can't reduce, and there you go. Or I guess you could have seen that 3 way back here, that this 3 goes into that 6 twice. And if you cancel there, you'd be left with 2/7. But however you see it. One thing here is, last example, root 12. 12 is not a perfect square, and again, you can't reduce 16 and 12 as a fraction because that's inside a radical and that's outside. 12 is not a perfect square, so you have two options really here. Some people will say, okay, I'm going to multiply by root 12 right away to rationalize that, and that would be totally fine. Other people will say 12 is not a perfect square, but I could I could reduce it a little bit because a perfect square does go into it. So I'm going to do that, but they're about the same amount of work either way. If you want to reduce the radical first, this is still 16 in top, but root 12 breaks down to root 4 times root 3. The square root of 4 is 2, so you really have 2 root 3. That's the simplified version of root 12. And now you might even notice, hey, I could divide 16 by 2 because that's now on the outside. 16 divided by 2 is 8 over root 3. And now you've sort of reduced the radical down to small as possible, but you're still left with a radical in the denominator. So we're going to multiply by root 3 over root 3 to rationalize it. And what do we get? 8 root 3 up top. Root 3 times root 3 is 3, and 8/3 does not reduce. There's your final answer. If you did want to do that first thing I had mentioned, because definitely people will do it, it's not bad, is, you see a radical, let me multiply by root 12, then you get 16 root 12 over 12 right off the bat. But then you've got all kinds of reducing to do. You've got 16/12 to reduce. They're both divisible by 4, and you get 4 root 12 over 3. Cool, but root 12 still reduces. The same root 12 that maybe you should have reduced at the beginning. Doesn't matter. Root 12 becomes 2 root 3. 2 root 3, but with the 4 out in front, gives you 8 root 3 over 3. Same answer, whatever you like. All right, kids, I hope you watch this all the way through because there are a lot of little twists with it, even though the concept is not too bad. So practice with it, take your time, check with a calculator if you like, and obviously ask me if you got any questions. Good luck, kids.